Okay, so from last time we implemented this guy here who's moving around using a velocity vector, and the keys over here are arrow keys. As I press them, they change his velocity vector, and then he's being pulled by gravity. So it's a little physics simulation. And you see if I let go of the keys, I'm going to press the up key and I let go, and gravity slowly takes over and he gets pulled down there. So if you remember, this line here handles the bouncing, or these lines here handle the bouncing against the sides, and then this one line here handles the gravity, and these ones change his velocity as I press the keys. So what I want to do is change this, so instead of always going down, is we're going to say, well, he's in space. He's in space, and there's the Earth, and he's actually getting pulled by the gravity of the Earth. Um, so what's the difference? Well, how do we do that? Let me explain using little pictures. I mean, so I'm gonna move this guy over here somewhere in there and stop him. Stop. And then, so what's happening right now is, right now, let's say, he's here, right? And so there's, say, his velocity is, say, going that way. Right, so that's down by these arrows. So I press the arrows, I change the velocity, it could be anywhere. And then when I get down here, I add it to the y velocity, I add -1. So that means I add this little arrow here. So I have this arrow, and then when I add that arrow, the resulting arrow, is this one. So he ends up moving from here to there. Right? So he has a velocity from the keyboard and then velocity of gravity. He moves there. So basically each time through the loop, no matter what his velocity is, I always add -0.1. So this one line of code is gravity. Right? That's how we are implementing gravity, just one line of code, which all it says is move every time the y velocity is going to go, it's going to decrease by 0.1. In this case, that's the magnitude of gravity that I chose. So all we have to do is, it's always pointing down because, we're assuming, the Earth is huge, right? This flat part is the Earth. Gravity always pulls down. The Earth is humongous. But now he's in space. So what's going to happen is gravity doesn't necessarily pull down. Gravity is going to pull towards Earth, right? So if he's here, gravity is going to pull here. But, if he was down here, gravity is going to pull here. If he was up here, gravity is going to go in this direction. But really, that's the only change we need to make. We just need to change the direction of gravity. Then, instead of, we can just add it right here. So all we need to do is figure out, what's this vector, what's this direction. Given that he is, at any point, wherever he is, I need to figure out what direction points me towards the Earth. And luckily, Scratch provides us with something we can use for that. And that is the point towards, right? So we have this, we can ask our guy, I'm going to get rid of gravity here. So first, let me get rid of gravity and show you if I get rid of gravity and I run it again, now he doesn't fall down, he just floats. So as I press these things, he's floating around, not falling down, he still bounces. So there's no gravity, so now he's in space, but he's not being attracted by the Earth. Right? So I want him to get pulled in by the Earth's gravity. So I'm going to put this here. I'm going to say, I'm going to ask him to point towards the Earth. Right, and then you have to make sure you go over here to the guy and then change his rotation style so that he can rotate. So this is his rotation here. Then stop, and go. I'm sorry, this is no rotate, this one's rotate. So okay, now he's rotating, and you can see he's always pointing towards the Earth. He's actually pointing with his left hand there. So if I move him down here, his left hand is now always pointing towards the Earth. Right? If you look over here, his direction, this direction is the angle, right? This direction is the angle that he's heading at. So that gives us the actual angle that he is currently at. And you'll notice that direction 0, as we go closer, we just passed it 0. So now it's negative and now it's positive. If we go under the earth, so he points towards it, it'll become 0 and then becomes positive. We can now, I think we can move this around. See, so there. So 0 is pointing right straight up, and then 90 degrees is that one, and minus 90 is pointing to the left, and then 180 or negative 180 is pointing down. So awesome. So all we need to do is get him to point towards the earth, right? And once he's pointing towards the earth, then the direction variable, which is what we've been looking at here, direction variable will give us that angle. So, okay, so now what the question is, we got this guy, oops, we got this guy, I'm gonna erase that. We got this guy now, and direction is the angle. So we have this angle here, and that's the variable direction. So all I need to do is figure out the components of this vector, the direction. So I need to figure out the x component and the y component, right? And how do I do that? Well, here's where trigonometry comes in, namely the unit circle. So if you can write over here, unit circle, and there's some very good Khan Academy videos on this. But the unit circle, we use it a lot when doing graphics. The unit circle is just a circle with a radius of 1, right? And it's centered at 0, 0 in the plane. So this point, 0, 0, that's the center of the circle. I know it doesn't look like a center, but pretend it is. And it is, minus 1 in the x direction. This point here is 1, and this point here is y equals 1, and this point here is y equals minus 1. So if you have a unit circle, then, and you have this angle here, this point right here has x and y coordinates. The x is the cosine of the angle here, theta, we'll call it theta. And y, the y coordinate of this point is the sine of that angle, theta. So to draw it over here bigger, because I ran out of space, we have this unit circle, this angle theta, this point here, xy, is given by cosine theta sine theta. The cosine and sine are two functions, mathematical functions, which are defined for us in every programming language. So there we go. So, and this is just what we needed, right? So the x is just going to be the cosine of the angle, and the y of this point here is going to be the y of the angle, right? So that's our forces. Let's go implement that. We just multiply it by whatever force we want. So I'm gonna actually use a block for this just to make it more understandable. And let's say I call it add force make block. I'm gonna call it the add force, and it's gonna actually, I'm gonna have it take two parameters. One is what's gonna be number inputs. One is gonna be the angle, that's the direction, and the other one is gonna be the magnitude. So that'll be the actual magnitude of the gravity. Magnitude. There you go. And so that's it. Don't need that. Okay, so let me see if I can put this here, throw away the old gravity. And like I said, all I need to do now is I'm going to change the x velocity and the y velocity. Yeah, by the way, I don't need these on floor. That's from an old. Okay, So the x velocity and the y velocity. So x is going to be the cosine of, so cosine, you have it here, right? That's the cosine of what? The direction variable. Well, actually, I'm going to be passing that as the angle variable. So you can do this, check this out. So the cosine of the angle variable. And we're gonna, that's gonna be a number between 0 and 1. You might want to increase that and decrease that by the magnitude. So the magnitude is just gonna be a number that tells us, how much gravity, how strong the gravity is. So I'm gonna do that. So the magnitude times the cosine of the angle. Try to put that in in there, which is gonna be tricky. There. And then you do it all over again for the other guy, for the y-axis. So multiply, except for the y, is going to be the sine of the angle times the magnitude. Okay, there you go. And so I point towards the earth, then I'm going to add a force equal to the angle is just the direction. So because, I made him point towards the earth, now the angle is the direction. And the magnitude is, whatever number, whatever force I want. Let's just start with 1. Let's see if that's strong enough. So stop it. Start it over again. And you see, I'm not pressing anything. See what happened? He kind of went to the left there. So I put it here. He looks like he's attracted to the earth, but then, wow, seems like he's getting repelled. So I put it over here. So I put it over here. Put it down and come on. Keeps moving, so it's hard to grab. Put it over here. He's attracted, then he's repelled. So what's going on here? Well, if you pay attention, you might have realized that, you see, the problem is a programming problem. It's not a math problem. The problem is that here, for in Scratch, the angle 0 points straight up, right? As you can see here, and 90 degrees is to the right, and to the left, pointing to the left, as I'm doing here, is minus 90, right? So so in Scratch, this is 0 degree angle. This angle here is 90 degrees, and this angle here is minus 90 degrees, and in between and so forth. Whereas in math, in the unit circle, like which you saw before, in the unit circle and in math, the unit circle 0 is this guy here. So this is 0. This angle here is 0. This angle here is positive 90. So sorry, 90. And this angle here is negative 90. So that's the problem. When if I just put in direction here, I put in direction as the angle, then that doesn't quite match, because Scratch's definition is when Scratch is 0. I really want it to be when Scratch is 0, says 0, that means the guy's pointing up. I really wanted to say 90, because when I apply the cosine, up is 90, right? This direction straight up plus 1 in the x direction is 90. So all I need to do is to change 0 to 90. If it gives me 90, that should be 0. If it gives me minus 90, that should be minus 180 or plus 180, because this angle is 180, and so forth. So if you think about that for a little bit, you realize that the function to do that is as follows. What we're going to do is, I'm going to I'm gonna create, I thought I deleted that. I'm gonna create a new variable called fixed angle, just for this guy here, right? And I'm gonna set inside this procedure here, I'm gonna set the fixed angle to be, and what I need to do is multiply the angle by -1 and then add 90 to it. If you look at the picture, multiply the angle by -1, and I did that wrong. You gotta be careful how you do that. I'm gonna multiply the angle by -1, and then to that I'm gonna add 90 degrees. So to look at the picture here, whoops. Right. So you'll notice that this is 0, so I have to add 90. To move the 0 over here, I gotta add 90. But also you notice when I do that, if I do that, then this is -90, but this is 90, right? So if I turn this to the side, it's still wrong because -90 would be over here, 90 would be here. So that's why I multiply by -1 to basically mirror this around. So that's my fixed angle. That's how I fix the angle. And then now I don't use the angle. Bye-bye. Throw that away. I'm going to use, oh, wait a minute, what happened there? This should go there, and this whole thing needs to go in there. Yep. So, and then I'm going to use, instead of the angle, I'm going to use the fixed angle. I need to show that. Oops. Fixed angle. Fixed angle there. Fixed angle. So there it is. This is my add force function. And I stop it and I turn it on, and you see now he's attracted, and he's in orbit. We can move the Earth around, he'll follow the Earth and try to get an orbit around it. Whoops, sorry. And go back here, see the code, and you see I can try to use the arrows to move him away, but it's hard because the gravity is pretty strong. So I can change the magnitude of the gravity here. So gravity is 1. I might want to change that to minus. Oh, that's negative gravity, so it's going to repel, which is something else you might want to do. If I reduce the gravity to 0.5, now that's less, and then maybe I can use the arrows to move them away, and they'll come back. Okay, now but a little bit of physics though. So here I am adding a gravity with the magnitude that is always the same, right? So that means that if he's out here, no matter how stop, no matter where he is, so he could be all the way out here, his force towards the Earth will be the same exactly. It'll be 0.5 every time. That's not how the real world works, actually. So what physics tells us is that the force of gravitation is the gravitational constant times the first mass times the second mass divided by the distance squared. So like for this simulation, I'm ignoring masses, and this is just a number, constant, so we can ignore that too. So Newton tells us that the force of gravity between two objects is basically 1 over their distance squared, or the square of the distance. The distance is the distance, the distance between the guy and the Earth. So that means that as he gets farther, this number gets bigger, so the force of gravity gets smaller. So this number should be 1 over the distance squared if this were to be like a real simulation. So let's try to do that. So all we have to do is change this 0.5 to be math operators. So we need division. It's going to be 1 over 1 divided by, and the distance to the Earth, luckily we have that, right? Where is it? Move turn point. There it is, distance to, so isn't the distance to the Earth. So 1 divided by the distance to the Earth, and to get square, we just have to multiply, the square is the distance times the distance. So we just say, distance to the Earth times the distance to the Earth. 1 over that is the force. Instead of saying 0.5, I'm going to say that. That's the force. And I'm going to stop it and start again. And you can see nothing's happening. So, because the force is actually, you can see there's a little bit. So, because the force drops off a lot as he gets closer, as he gets farther away, there's very little force. Now you can make this bigger. Instead of 1, we can make that a big number. And then that's too big. About 10. So you can play around with that. So you can see as you get closer. If I don't press anything, it doesn't look like. So now I'm not pressing anything, and it's very hard to see the effect of the force, because really it drops off so significantly as he gets farther away. So it has to be really close, like there. See, you could saw it with 100. So for this game, even though this is how the real world works, like the force of gravity drops as the square of the distance. That means that if he's over here, there's almost no force, and he has to be really, really close to the Earth to feel the force of it. So in terms of making the game fun, it's probably better to just do this. Instead of the square of the distance, just the distance, and then maybe instead of 110. So that way he can feel the force of the Earth, the gravitational pull, when he's farther. So there you see, he felt that. So it's kind of fun. You can move him well, and he pulls in again. If you try, you might be able to get him into an orbit. There he is. I'm not touching anything. So he gets into an orbit like a satellite might. And one last thing, and if you click here, you stop him from rotating, then and I think that looks better. He's still pointing, he's just, you can't see the fact that he's pointing. You can see here the direction he is changing, it's just not getting reflected. So there it is. Another fun thing to do is you can add, you see I just did point towards Earth and then add force. You could create an, say a sun. You could add another sprite for the sun, and then after you do this, you can say, okay, now point towards the sun, and then add the force distance to the sun in that case, and now you have 2 bodies, right? So you can add any number of bodies, the Earth, the sun, or different planets. You can change this to be the negatives, and then he would get repelled. So lots of fun things you can do with this.